So welcome students. Let us look at the topic of logarithms. So the first question that we need to answer is, what is logarithm? What is logarithm? And how do I understand it? How do I understand it? So these are the basic questions that we are going to deal in this video. So first, to understand logarithms, you need to know basic knowledge about the topic of indices or exponentiation. So I hope you know some basics about indices. So this indices is a very basic topic that you learn in your lower classes. For example, what is 2 power 1? 2 power 1 is equal to 2, right? And if I ask you what is 2 square, it's very easy to answer. 2 square, you have already learned it as 4. Similarly, what is 2 cube? I'll write some expressions. I'll write some equations in indices. So 2 cube is equal to 8, right? 2 power 4 is equal to 16, right? Similarly, I'll write some powers of 5 also. So 5 power 1 is equal to 5. 5 square, you know it as 25. 5 cube, you know it as 125. 5 power 4, you know it as 625. So it's very easy to raise a positive number to integer power. I can also write 2 power 0, 2 power minus 1 also if I want. That's very easy to find. Now, so these are some equations in exponential form. And in this exponential equation, we have some terms. This number is called the base. And this number is called the power, right? So we raise a base to a certain power. Or this can also be called exponent. Same. So also called exponent. This is also called index. 2 raised to the power 2, 2 raised to the exponent 2, 2 raised to the index 2. Similarly, 2 raised to the power 3, 2 raised to the exponent 3, 2 raised to the index 3. So you can, whatever you want, you can tell. So 2 raised to 3 is equal to 8. Similarly, 5 raised to 3 is 125. Now, these are the equations that you come across in the topic of indices. And we also learn the properties of indices. Now, I'll ask you a similar question, but in a reverse way. The question is, what is the power of 2? What is the power of 2 present in 2? What is the power of 2 present in 2? If I ask you this question, what will be your answer? So in 2, what is the power of 2 present? Or to what power 2 has to be raised to get 2 as the answer? So we know that 2 has to be raised to the power 1. So power of 2 present in 2 is 1, or power to which this base 2 has to be raised to get the answer as 2 is equal to 1. Now, can I write it? Can I write the same equation like this? What is the power to which the base 2 has to be raised to get 4 as the answer? So what is the power to which base 2 has to be raised to get 4 as the answer? The answer should be 2. And if I write the same thing here, what is the power to which base 2 has to be raised to get 8 as the answer? The answer should be 3, right? 2 has to be raised to the power 3 to get 8 as the answer. Similarly, let me write this expression for each and every equation. So you have to be very careful and you have to observe this equation very carefully. What is the power to which the base 2 has to be raised to get 16 as the answer? The answer should be 4. Now let's do the same thing here. So what is the power to which the base 5 has to be raised to get 5 as the answer? The answer is 1. what is the power to which base 5 has to be raised to get 25 as the answer? The answer is 2. What is the power to which base 5 has to be raised to get 125 as the answer? The answer is 3. Similarly, the power to which the base 5 has to be raised to get 625 as the answer is 4. So I hope you have understood this converse way of writing the same equation. Now, if you want to understand logarithms, you just need to understand logarithm as exactly same as this power. So log is exactly same as this POW that I have written. So what we do in log is, if I write log of 729 to the base 3, if I ask you what the value of log of 729 to the base 3, this is exactly same as the power to which base 3 has to be raised to get 729 as the answer. So we know that this is equal to, so 3 power 4 is 81, 3 power 5 is 243, 3 power 6 is 729. That is, 3 has to be raised to the power of 6 to get the value, to get the answer as 729. So if you can understand what this power is doing, this is same as the log term. This is what log actually does. It calculates the power to which the base has to be raised to get the answer, which is this number. So I hope you have understood what logarithm basically does. So now let us go forward and look at further understanding of logarithms. So the most basic formula that you need to master in logarithms is how to convert a given equation in exponential form to the corresponding equation in logarithmic form. So if you have an equation a power x is equal to y. So a raised to the power x is equal to y. So this is an exponential equation. So this can be written in logarithmic form as log of y to the base a is equal to x. That is, the base a needs to be raised to the power x to get y as the answer. So a raised to power x gives y. The power to which a has to be raised, the power to which base a has to be raised to get y as the answer is equal to x. So these two equations represent the same information. And as you can very clearly see, the base in the exponent form becomes the base of the logarithm. So this is called the base of the logarithm. Just these two numbers will get reversed. So a power x is equal to y. So log y to the base a becomes equal to x. So this is how the logarithmic conversion looks like. If 6 power 2 is equal to 36, if this is the equation in exponential form, the corresponding logarithmic form is log, this base remains the base of log, this is the base of exponential, this is also base of logarithm, the base does not change, just these two numbers get exchanged. So log to the base 6 of 36 is equal to 2. That is, 6 has to be raised to the power 2 to get 36 as the answer. So if you have something like 4 power 3 is equal to 64. So the logarithmic form of this equation is log 64 to the base 4 is equal to 3. Log 64 to the base 4 is equal to 3. So similarly, if you have log 100 to the base 10 is equal to 2. So what is the corresponding exponential form? 10 power 2 is equal to 100. 10 power 2 is equal to 100. This is the exponential form. This is the logarithmic form. Right? Next, similarly, you can write the corresponding logarithmic forms and exponential forms of any equations. So now let us look at some examples. So if I asked you to find these values, so what is log 64 to the base 2? So what I am effectively asking you is to what power should 2 be raised to get 64 as the answer? So initially what we do is, we convert this equation into exponential form and try to solve it, because exponential form is much more familiar than logarithmic form for now. But once you have understood logs, you will be able to do it directly. So for now, what I do is, I'll assume this as x. So log 64 to the base 2, let it be equal to x. And this implies, if this is equal to x, then if you convert this into exponential form, 2 power x has to be equal to 64. And this implies 2 power x has to be equal to 2 power 6. 64 is 2 power 6. And this implies x is equal to 6. That means the value of log 64 to the base 2 is equal to 6. And this is very clear initially also. 2 has to be raised to the power 6 to get 64. We know that. Next, so if you have something like this, log 10 power 6 to the base 10. So again, the question is, to what power should 10 be raised to get 10 power 6 as the answer? The answer is, I hope, very clear. The answer should be 6, right? 10 has to be raised to the power 6 to get 10 power 6. So that's very clear. You can also do it by the above process. Get 6 as the answer. Next, what is log root 2 to the base 2? So to what power 2 has to be raised to get root 2 as the answer? So till now we are having nice natural numbers in this place, but it's not necessary that always this has to be a natural number. This can be rational, irrational also. So what is log root 2 to the base 2? Let's say let it be equal to x. And this implies the exponential form of this is 2 power x has to be equal to root 2. And this implies 2 power x has to be equal to, the root 2 is nothing but 2 power half. And this implies x is equal to half. This implies x is equal to half. That means log root 2 to the base 2 is equal to half. And now let us go to this question. What is log root 3 to the base 9? To what power 9 has to be raised to get root 3 as the answer? Again, initially let it be equal to x. This implies 9 power x has to be equal to root 3. And this implies 9 is 3 square. So 3 square power x has to be equal to 3 power half. 3 power half. This implies 3 power 2x has to be equal to 3 power half. And by equating the power, because the base is same, the powers has to be same. 2x is equal to half. This implies x is equal to 1 by 4. So that means the value of this is equal to 1 by 4. This 9 has to be raised to the power 1 by 4 to get root 3 as the answer. Next, finally, let us take log 125 to the base root 5. So again, let it be equal to x. This implies root 5 power x has to be equal to 125. So let us express both of them in powers of 5. This implies 5 power x by 2. Root is power half. 5 power x by 2 is equal to 5 power 3. 125 is nothing but 5 cubed. This implies x by 2 is equal to 3. And this implies x is equal to 6. So the value of log 125 to the base root 5 is equal to 6. So the next topic that we're going to learn is validity of logarithm. Here, the thing that you need to understand is that logarithm cannot be calculated for every number. So let us try to analyze this statement. So first, let us consider different powers of the base 2. So let us raise 2 to different powers. So we know that 2 power 0 is equal to 1. 2 power 1 is equal to 2. 2 square is equal to 4. 2 cube is equal to 8. 2 power minus 1 is half. 2 power minus 2 is 1 by 2 square, which is 1 by 4. So if you observe the answers that you get as I raise 2 to different powers. So 2 power 0, 2 power 1. So I can also raise 2 to the power half. 2 to the power half will be equal to root 2. So if I raise 2 power 0, the answer is 1. 2 power 1 is 2. If I raise 2 to any number between 0 and 1, I get some answer between 1 and 2. Similarly, 2 power 1 is 2, 2 square is 4. So if I raise 2 to any number between 1 and 2, that is 2 power 3 by 2, or any other number between 1 and 2, 1.3, 1.4, so on. So you get numbers between 2 and 4. Similarly, if I go to the negative side, 2 power minus 1 is 1 by 2. So if I raise 2 to any number between 0 and minus 1, I get numbers between 1 and half. So similarly, half and 1/4, so on. So what you need to observe here is 2 is the base can be raised to both positive and negative powers. To both positive and negative powers. That is, you can raise 2 to any real number. And the answers that you get, as you can see, the answers that you get, the values of power of 2 are always positive, if you see. So 2 raised to the power positive numbers is also positive. 2 raised to negative numbers is not negative. The final answer is positive. So 2 can be raised to both positive powers as well as negative powers, but the answers that you get, the values of the powers of 2 are always positive. And as you go to 2 power infinity, so as you go on increasing the power, 2 power infinity is nothing but infinity. And as you go on going to the negative powers, 2 power minus infinity is nothing but 1 by 2 power infinity. That is nothing but 1 by a very large number, approximately tending to 0. Right? So the values of the powers of 2 go from 0 to infinity. It will never be equal to 0, but it goes closer and closer to 0 and goes till infinity. So I hope you have understood what powers that the base can be raised. The base can be raised to both positive and negative powers. This every real power, fractional powers, irrational powers, any power can be raised. And the answers that you get are always between 0 and infinity. Now if I ask you to find log of minus 2 to the base 2, what is the meaning of this? To which power 2 has to be raised to get minus 2 as the answer? So as you can see from this table, can 2 be raised to any power such that you get minus 2 as the answer? No, because whatever power you raise 2 with, the answer is always positive. So log of minus 2 to the base 2 is not defined. Similarly, log 0 to the base 2. Log 0 to the base 2. So to which power 2 has to be raised to get 0 as the answer? It has to be minus infinity. But minus infinity is not a finite number. That means there is no finite answer to this question. This is also not defined. So if I have to write, I'll write that this tends to minus infinity. This goes till minus infinity. But effectively, exactly 0 is not defined. So log to the base 2 is not defined for negative numbers and is not defined for 0 also. So logarithm to some base will be defined only for positive numbers, positive real numbers. That is, log x to the base a is defined only if x is positive. That is 0 to infinity, not 0, it should be more than 0 and it can go till infinity. It can be any positive number. So in terms of this number, this has to be positive. That is, this has to be greater than 0 for logarithm to be defined. So now let us analyze what should be the values of bases for which logarithms are continuously defined. So now if you look at the problematic bases, so you encounter 3 types of problematic bases. One is the negative numbers, 0 is problematic, 1 is problematic. So if you take negative number, so negative number can be raised to integer power, there is no problem. So minus 2 power 0 is 1, minus 2 power 1 is minus 2, minus 2 whole square is 4, minus 2 power minus 1 is 1 by minus 2, which is minus 1 by 2, minus 2 to the power minus 2 is plus 1 by 4, so on. So when you raise a negative number to integral power, there is no problem. But if you want to power negative number to fractional powers, so you have a problem. For example, if you take minus 2 power half, so you take a power between 0 and 1, let us take it as half. So minus 2 power half is nothing but minus 2 power half is nothing but square root of minus 2, which is not defined. Minus 2 power 1 by 3 is defined. There is no problem with this. So minus 2 is not defined for every number. Minus 2 power something is not defined for every number between 0 to 1. For some numbers it will be defined, for some numbers it will not be defined. So if I ask logarithm of exactly minus 2 to the base minus 2, the answer can be thought of as 1. But if I write a different number, here, different positive number here, if I write log plus 2 to the base minus 2, don't have an answer, because minus 2 cannot be raised to any power to give plus 2 as the answer. Cannot get plus 2 whatsoever the power is. That means this is not defined. So the first problem with negative basis is, for some numbers logarithm is defined, for some numbers logarithm is not defined. So what we do is, when you define log, we exclude negative bases. We say that negative bases are not allowed in logarithms. And similarly, zero base is not allowed, because 0 to the power any number is always 0. And if you take 0 power 0, 0 power 0 is undefined. 0 power any positive number is equal to 0. And 0 power negative numbers is again undefined, because 0 power negative numbers is 1 by 0 power positive numbers. So this gives you 1 by 0. That is something like 0 power minus 1. By definition is 1 by 0, which is not defined. So that means even for power, even if the base is 0, for some powers it is defined, for some powers it is not defined. And if I ask you what is log 5 to the base 0, log 5 to the base 0, what power 0 has to be raised to get 5 as the answer? No. Cannot get anything, because 0 power any number is 0. So log 5 to the base 0 is not defined. So 0 is one of the problematic base. So the base cannot be negative, cannot be 0 also. So can it be any positive number? Again, among all the positive numbers, 1 is a problematic base. Because 1 power any number, 1 power any number, 1 power 0, 1 power 1, 1 square, 1 power minus 1, 1 power minus 2 are all equal to 1. So 1 to power any base, any power is equal to 1. So if I ask you log 121 to the base 1, what should be the answer? There is no answer, because 121, whatever power you give to 1, you always get 1 as the answer. Can you get 121 as the answer? No. It is not defined. So keeping in mind these problems, so when you define log x to the base a, I write that the base a should be greater than 0 and base a is not equal to 1. This is about the base, and the argument which is here, x, should be positive. So with these conditions, we define the logarithm. So whenever you encounter logarithm, the base has to be positive and not equal to 1, and the argument which comes inside log has to be positive. These are two things which you need to remember. So now let us look at how the values of logarithm changes as x changes. So if you increase this x, will the value of logarithm increase or decrease? So let us look at the base as 2. Let us take the base as 2. So log 1 to the base 2, log 2 to the base 2, log 4 to the base 2, log 8 to the base 2, so on. Log 1 by 2 to the base 2, log 1 by 4 to the base 2, so on. So as you can very clearly see, in this case I am increasing the value of x slowly. So the value of x, 1 by 4, 1 by 2, 1, 2, 4, 8, the value of x is increasing slowly. Now what are the values of logarithms? So log 1 to the base 2. So 1 can be written as 2 power 0. So what is the power of 2 present in 1? That's nothing but 0. So 2 has to be raised to the power 0 to get 1. So what is log 2 to the base 2? To what power? 2 should be raised to get 2 as the answer. 1 is the answer. What is log 4 to the base 2? 2 is the answer. Log 8 to the base 2 is 3. Log half to the base 2 is obviously minus 1 because half is nothing but 2 power minus 1. Log 1/4 to the base 2 is minus 2, so on. So as you can very clearly see, as the value of x is increasing, the value of y is also increasing. That is, if you increase the value of the number here, the value of logarithm increases. For base 2. For base 2. Now, does this always happen? So we can see that the values of base can be in between 0 to 1 or 1 to infinity. There are two separate blocks of bases possible. That is, the bases can be in between 0 to 1 or they can go from 1 to infinity. Now our base 2 lies in this block. So if the base lies in this block, that is, if the base is greater than 1, as x increases, log x to the base a also increases. So now let us take a base in this block. Let us take half. Let us take half as the base. So let us do everything again. Log 0 to the base half, log 2 to the base half, log 4 to the base half, log 1 by 2 to the base half, log 1 by 4 to the base half, so on. So let us try to calculate these numbers. Now what is the first number? 1. 0 cannot be written in the place of this. So log 1 to the base half. Half should be raised to which power to get 1 as the answer? 0. Half to the power what is 2? So obviously half to the power minus 1 is 2. Half to the power minus 2 is 4. Half to the power 1 is half. Half to the power 2 is 1/4, so on. So can you see that this follows a reverse order as x increases? So here 1/4, half, 1, 2, 4, these numbers are increasing, but these numbers are decreasing. 2, 1, 0, minus 1, minus 2. So as x is increasing, the value of y is decreasing, the value of log is decreasing. That is, if the base is in between 0 and 1, if the base is a fraction, then as x increases, log x to the base a has to decrease. As x increases, log x to the base a decreases. So this is the pattern in which log changes as the number inside log changes. You need to remember it in 2 steps. If the base is greater than 1, then as x increases, log x increases. If the base is in between 0 to 1, as x increases, the value of log x decreases. So now that you have understood the concept of logarithm, most useful base in number theory for logarithms is log x to the base 10. 10 is the most useful base that will come across a lot of problems. So what has been done is 10 has been decided as the default base of a logarithm. That is, if I write just log x without writing any base, that means the default base has to be default base is equal to 10. This has been decided. This is a convention. And this type of logarithms are called common logarithms. So if I don't write any base to log, you have to take the default base as 10. And 10 is the most used logarithm in algebra and number theory. In calculus also we use the concept of logarithms. So once you go to the topic of calculus, you go to something called logarithmic functions. Let us see what these are. So, and in calculus, you'll observe that instead of 10, there is a very useful base which is called e. So log x to the base e. In calculus, we take log to the base e as the default base. And instead of writing log x here, we write it as ln x. We use the term natural logarithm. So, and we write it as ln x. Ln x represents the natural logarithm of x. And whenever you write this, the default base is e. So you might be wondering what e is. E is a very interesting number. It's an irrational number. And whose value is somewhere like 2.71828482, so on. So you have e as an irrational number. This is a very interesting number. There is a story of e which can be seen in the videos on the number e. So for now, what you need to understand is, if you have a common logarithm, the default base is 10. If you have a natural logarithm, the default base is e. So the next topic is the properties of logarithms. This is the most important topic and which will be useful for you in solving a lot of problems. So the properties are divided into different sets. The first set of properties are log ab to the base c. If you have a product of two numbers inside log, I can write as log a to the base c plus log b to the base c. That is log 2 into 3 to any base is equal to log 2 to the same base plus log 3 to the same base. So this is the first property which is called the product rule. For example, log 6 to the base 5 can be written as log 2 to the base 5 plus log 3 to the base 5. So this can be written as log 2 to the base 5 plus log 3 to the base 5 because 6 is 2 into 3. So when you split the log of a product, the logarithms have to be, individual logarithms have to be added. And the second property is log a by b to the base c. Something like log 2 by 3 to the base 5 can be written as log 2 to the base 5 minus log 3 to the base 5. So log 2 by 3 to the base c is log 2 to the base 3 minus log 3 to the base c. A by b you have log a minus log b. These two are the most important. So log ab is log a plus log b. Log a by b is log a minus log b. And the third property is called power rule, which says that log a to the power m to the base c is m log a to the base c. This power of this number just comes out as the multiple. So log a to the power m to the base c is m times log a to the base c. The power just comes out here. And log a to the base c power m, if you have power in the base, this will come out as 1 by m. This will come out as 1 by m. So the power of the number above will directly come out of the logarithm. The power of the base will come out as a reciprocal. This is called the power rule. For example, log 2 cubed to the base 3 can be written as 3 times log 2 to the base 3. So this power of 2 will just come out 3 times log 2 to the base 3. Similarly, if you have log 3 to the base 9, this can be written as log 3 to the base 3 square. So here the power is for the base. So this comes out as the reciprocal 1 by 2 times log 3 to the base 3, which is equal to 1, that is equal to 1 by 2. So log 3 to the base 9 will be equal to 1 by 2. So what are the properties? Log ab is log a plus log b, log a by b is log a minus log b, and the power of the number, the power of the argument comes out directly. The power of the base comes out as the reciprocal. So these three constitutes the first set of properties. So the next set of properties that we learn are called base change formula. So in this you have three formulae. First is log a to the base b can be written as log a by log b to the same base, any common base. So log a to the base b can be written as log a to some base c by log b to the same base c. So definitely if you have log a by log b to the same base, this C and C gets cancelled and B goes to the base here. That is log A to the base B. Similarly, in multiplication, log A to the base B can be written as log A to the base C into log C to the base B. Here C and C gets cancelled and B comes here. So effectively this is not getting cancelled, but in some way, to remember this, you can think of these getting cancelled and B coming here. And log A to the base B can be written as 1 by log B to the base A. So if you want to take this to the denominator, you just need to interchange the base and the argument. So for example, log 2 to the base 3 can be written as 1 by log 3 to the base 2. In some problems, you would be required to do this. So just keep in mind that this can be done. And if you want log 2 to the base 3 into log 3 to the base 2, the answer will be this 3 and this 3 gets cancelled and 2 comes here. It is same as log 2 to the base 2, which is equal to 1. So log 2 to the base 3 is equal to 1 by log 3 to the base 2. So this can be done. And if you cross multiply this, log 2 to the base 3 into log 3 to the base 2, this 3 and 3 gets cancelled. You get log 2 to the base 2, which is equal to 1. So effectively these two are similar. This property is a sub-property of this general property. So these three properties are called base change formulas. So log A to the base B can be written as log A by log B to any common base. Log A to the base B can be written as log A to C into log C to B. Log A to the base B is 1 by log B to the base A. So the next and last set of formulas are called simplification formula. So here also you have three of them. So the first property is log A to the same base A. So if you have the same number in the base as well as argument, the answer will always be equal to 1. And if you have 1, the argument log 1 to any base is equal to 0. So log 1 to any base is equal to 0. Log A to the same base A is equal to 1. So these are very straightforward because the power of A that is present in A is equal to 1. Power of A present in 1 is equal to 0. Next, these two are interesting formula. So A power log x to the base A is equal to x. So if you have A in the base and in the power, if you have also A in the base. So these two bases, everything will get cancelled out and you get x as the answer. So this is a very interesting property. So why does this work? What is log x to the base A? What is log x to the base A? This is the power to which A has to be raised to get x. This is the power to which A has to be raised to get x as the answer, right? This is the power to which A has to be raised to get x as the answer. Now, if I raise A to exactly this power, what do you get? You have to get x, right? So this is the power to which A has to be raised to get x, and I'm actually raising A to that power, so you're getting x as the answer. And this is a very important property and will be useful in drastic simplification. So A power log x to the same base A, if you have the same base here and here, so you get x as the answer. That is, if you have 10 power log 3, this is nothing but 3 because this is a common logarithm. The default base is 10. Base is 10, the default base is 10, so everything will get cancelled out. You get 3 as the answer. And sometimes you have an expression like this. So A power log x to a different base. So if these two bases are same, then everything will get cancelled out and you get x as the answer. If these two bases are not same, then the property says that you can exchange these two values. You can exchange A with x. So x can be brought down and A can be brought up. Something like you have 3 power log 15 to the base 9. So if you're asked to evaluate this, log 15 to the base 9 is not easy to evaluate. So this can be written as, so this 15 and 3 can be exchanged So this will be 15 power log 3 to the base 9. That is equal to 15 power log 3 to the base 9 can be written as 3 square. This 2 can be brought out as 1 by 2 because this is the power of the base. So 15 power 1 by 2 log 3 to the base 3, which is equal to 1. That is 15 power half is equal to root 15. So 3 power log 15 to the base 9 will be equal to root 15. So this is how we use this formula to simplify the expressions. So there are a total of 9 formulas which you need to remember in 3 sets. So the first is product rule, quotient rule and power rule. And the next set of formulas are called base change formulas. The third set of formulas are called simplification formulas. So once you master these 9 formulae, theoretically you can do any problem in logarithms. So let us look at a sample question, logarithms. So it's given that log 2 to the base 10 is equal to x, and formulae, theoretically you can do any problem in sample question, logarithms. So it's given that log 2 to the base 10 is equal to x, and formulae, theoretically you can do any problem in logarithms. So it's given that log 2 to the base 10 is equal to x, and so it's given that log 2 to the base 10 is equal to x, and so it's given that log 2 to the base 10 is equal to x, and so it's given that log 2 to the base 10 is equal to x, and so it's given that log 2 to the base 10 is equal to x, and so it's given that log 2 to the base 10 is equal to x, and so it's given that 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 and log 10 cube to the base 10, that is log 1000 to the base 10 is equal to 3, and so on. Now if I ask you a question, what is logarithm of 25? So as you can see, 25 lies between 10 and 100, right? So 25 lies between 10 and 100. So log 25 lies between log 10 and log 100, right? So log 25 lies between log 10 and log 100. And what is log 10? It's 1. Log 100 is 2. It is log 25 lies between 1 and 2. So log 25 will be of the form 1 point, there will be some decimals, let us say A, B, C, so on. 1 point A, B, C, so on. Now you have an integral part of this number and a decimal part of this number. So this can be written as 1 plus 0 point A, B, C, so on. 0 point A, B, C, so on. So this part is called the characteristic part and the decimal part is called the mantissa. So whenever you calculate log of any number, if you get something point something else, the integer part of the number is called the characteristic and the decimal part of the number is called mantissa. For example, log 2 to the base 10 is equal to 0.3010, so on. These are the first 4 digits. So this implies the characteristic of log 2 to the base 10, the characteristic is 0 and the mantissa is 0.3010. It's as simple as that. So whenever you calculate the characteristic of some number, some log, you just need to find the logarithm. So whatever is the number before the decimal point, that is the characteristic. Whatever is the number after the decimal part, it is the mantissa. And one of the important things that you need to remember is that mantissa of a logarithm is always positive. Always positive. And if you take some log x, if the characteristic of this log is c and the mantissa of this log is m, then c plus m should give you the value of log x. So now, if log x, if logarithm of some number is equal to 2.313, if logarithm of some number is 2.313, the characteristic of this logarithm will be equal to 2, that is the number before the decimal point, and the mantissa will be equal to 0.313. If the value of logarithm is positive, the understanding is quite simple. So now let us go to a special case where the value of logarithm is negative. We have seen that the values of logarithms can be positive or negative. So let us say that log x is equal to minus 1.4. Minus 1.4. So what is the characteristic of it? So if I write the characteristic as minus 1 and the mantissa as 0.4, it leads to contradiction. This is wrong, because if characteristic is minus 1 and mantissa is 0.4, what should be the value of log? Minus 1 plus 0.4, which is equal to minus 0.6. So if log x is minus 0.6, then the characteristic will be minus 1 and mantissa will be 0.4. So if log is minus 1.4, so what we do is the characteristic of this is 1 less than minus 1, that is the characteristic is minus 2 and mantissa is written as the complement of 0.4, that is 1 minus 0.4, which is 0.6. So the characteristic of minus 1.4 is minus 2 and the mantissa is 0.6. Similarly, if log x is equal to minus 2.35, the characteristic of this logarithm will be -3, not -2. And the mantissa will be equal to the complement of 0.35, that is 1 minus 0.35, which is 0.65. Such that once you add these two, you get the value -2.35. So these are the two things that you need to remember about the characteristic and mantissa. First is mantissa is always positive, and the value of logarithm of any number has to be same as the characteristic plus mantissa of that logarithm. So next, where does characteristic of a logarithm becomes important? So in which type of problem that does characteristic become important? So one of the most important type of problem that you can solve is the number of digits. So if you want to find the number of digits in some very large number, if I say 2 power 56. So if you raise 2 to the power 56, it gives you a very large number. And if I ask you how many digits are there in 2 power 56? So this is one of the questions which you can solve using the concept of characteristic of a logarithm. And the next question is the number of zeros. The number of zeros after the decimal point, in 1 by 2 power 65. So if you take 1 by 2 power 65, it's a very, very small number, 0.00000, have a lot of zeros, and then finally you have some number. So if I ask you how many zeros are there just after the decimal point before the non-zero number starts. So these are two types of problems where the characteristic becomes important. So let us try to analyze how characteristic becomes important in these type of problems. So if I take log of 25 to the base 10, if I find log of any number to the base 10. So this can be written as log of, so this number can always be written in the form of something like this, 2.5 into 10 power 1 to the base 10. So I can always make this number in between 1 and 10. So I can always bring this number between 1 and 10 and write an appropriate power of 10 after that. For example, if you have 256, I can always write it as 2.56 into 10 square. If I have 0.25, I can write as 2.5 into 10 power minus 1. So I can always use appropriate powers of 10 and bring this number between 1 and 10. And what I do is now I'll separate it using the properties of logarithms. 2.5 to the base 10 plus log 10 to the base 10. And if this number is in between 1 and 10, if some number is in between 1 and 10, log of that number will be in between log 1, 0 and log 10, 1. That means if x is in between 1 and 10, log x is in between 0 and 1. That is, this has to be of the form 0 point something. So this number will always be of the form 0 point some number plus log 10 to the base 10 is 1. So the characteristic will be this power of 10 whatever you get plus, and whatever number you get here will be the mantissa of the logarithm. So as you can very clearly see, the power of 10 that you get here will be the characteristic, and the number that you get here, log 2.5 to the base 10, will be a decimal, and that will be the mantissa of that number. Now, how is this characteristic related to the number of digits? If 25 has 2 digits, the characteristic will be equal to 1. So let us take log 256. So if the number has 3 digits, so this can be written as log 2.56 plus log 100. Log 100 is nothing but 2. So this will be 2 point something. So if there are 3 digits, the value of logarithm will be 2 point something. That is, the characteristic will be 2. If the number is 2566, so log 2566 So this can be written as log 2.566 into 10 cubed. So this will be 3 point something. So can you see the pattern here? If there are 2 digits, then the characteristic of the logarithm will be equal to 1. If there are 3 digits, then the characteristic is equal to 2. If there are 4 digits, the characteristic is equal to 3. Hence, if you want the number of digits in any number, so the number of digits in x, so number of digits in a number x is nothing but the characteristic of log x to the base 10 plus 1. So this is the formula for number of digits in any number. So if you have a very big number, so if you want the number of digits, so what you just need to do is you just need to calculate the log of this. You find the characteristic and add 1 to that. So next, let us try to see the pattern for the number of zeros immediately succeeding the decimal point. So let us take an example. What is log 0.5 to the base 10? This can be written as log of 5 into 10 power minus 1 to the base 10. That is equal to log 5 to the base 10 plus log 10 power minus 1 is nothing but minus 1. Hence the characteristic will be equal to minus 1 and the mantissa will be equal to log 5 to the base 10. So similarly for this, the characteristic will be equal to minus 2 and the mantissa will be equal to log 5 to the base 10. And similarly in this case minus 3 plus log 5 to the base 10. Now as you can very clearly see, if there is no 0 just after the decimal point, you get characteristic as minus 1. So if you have 1 0, the characteristic is minus 2. If you have 2 zeros, the characteristic is minus 3. So if you want the number of the zeros immediately after the decimal point, you just need to find the characteristic of this and take the modulus of characteristic. It is the absolute value. You just remove the sign. So whatever you get is the mod of characteristic, and if you subtract 1 from that, you get the number of zeros. So the number of zeros in 0.005 immediately after the decimal point is nothing but modulus of minus 3, which is 3 minus 1. Modulus of minus 2 minus 1, that is 2 minus 1, 3 minus 1, so on. So mod C minus 1 is the number of zeros immediately after the decimal point. These are the two formulas. The number of digits in any number, is nothing but the characteristic of that number plus 1, and the number of zeros immediately after the decimal point of any small number is nothing but mod of characteristic minus 1. These are the two formulas which you need to remember. So let us take an example. So in a given question, you are given that log 2 to the base 10 is 0.3010. This information is given to you. Using this information, can you calculate the number of digits in 2 power 56? Let's take the same example. So if you want to solve this question, what you need to do is, if I want the number of digits in a number x, I need to calculate log x. So first we'll calculate log 2 power 56 to the base 10. This is nothing but 56 times this power goes outside. 56 times log 2 to the base 10 is 0.3010. 56 times 0.3010. So that is nothing but you just need to multiply these two. 0.3010 times 56, 0, 6, 0, 18, 0, 5, 0, 15. So 16.856. So the value of this logarithm is 16.856. So what is the characteristic of this? The characteristic is nothing but 16. So the number of digits is nothing but, by the formula, the characteristic plus 1. That is 16 plus 1 is 17. So the number of digits in 2 power 56 will be 17 digits. So looks simple, right? Now let's go to the next question. I want the number of zeros immediately succeeding the decimal point in 1 by 2 power 63. So to find that, first let us find the value of this logarithm. So log of 1 by 2 power 63 is nothing but 2 power minus 63 to the base 10. That is minus 63 times log 2 to the base 10 is 0.3010. Right? So 63 into 3 is 189. So this will be something like minus 18.9 so on. This will be minus 18.9. I'll just calculate this nicely. So 63, so 0309, 06018, so 036981. So 18.9630. So the value of logarithm is minus 18.9630. So what is the characteristic of this? The characteristic, because this is a negative number we have already seen, it will be 1 unit backwards. The characteristic is minus 90. The characteristic is minus 90. So the number of zeros immediately after the decimal point is nothing but mod c minus 1, right? Mod c minus 1. That is nothing but modulus of c is 90 minus 1 is equal to 80. So in another way, this is nothing but whatever number you get here, that will be the number of zeros immediately after the decimal point. So you can remember it as you want. So you can calculate the characteristic by taking the number before this number and then subtract 1 from that after taking the modulus, or you can directly report this number as the number of zeros. So in this video, let us look at what anti-log is. So as the name suggests, anti-log is the reverse of logarithm. So if log 2 to the base 10 is equal to 0.3010. So if log of this number to the base 10 is 0.3010, so what is the anti-log of 0.3010 with respect to 10? The anti-log of 0.3010 with respect to 10 is nothing but 2. So if log of 2 to the base 10 is 0.3010, what it says anti-log of 0.3010 with respect to 10 is nothing but 2. And as you can understand, what is anti-log actually doing? Anti-log is just 10 raised to the number. So anti-log of 0.3010, anti-log of 0.3010 is nothing but 10 power 0.3010. Because we have already seen in the starting that log is the reverse of exponentiation. So if log x to the base 10 is y, the anti-log of y is nothing but x. So if log x to the base a is y. So usually when you calculate anti-log, we take the base as 10. So if log x to the base 10 is y, anti-log of y is equal to x. And anti-log of y is nothing but 10 power y. So 10 raised to the power 10 raised to the given number is called the anti-log of that number. So whenever you see the tables of logarithms, so the first log tables give you log of some number to the base 10. And anti-log tables will give you 10 raised to that number. So I hope you have understood anti-log is nothing but 10 power the number. The last topic of logarithms is the logarithmic function. This is the topic that you get in 11th class. Till now, whatever we have studied, you're supposed to know in your classes till your 10th class. And this logarithmic function is introduced to you in the 11th class. So what is the logarithmic function? The function y is equal to log x to the base a is called the logarithmic function. In this function, x is always positive, that is x is always greater than 0, and the base is greater than 0 and base is not equal to 1. So why this happens we have already seen before. So the argument inside log has to be positive and the base has to be greater than 0 and not equal to 1. So y is equal to log x to the base a is called the logarithmic function. So what should you understand about the logarithmic function? So first, whenever I talk about function, you need to understand the domain and range of this function. So the domain is nothing but the values of x that can go inside the log function. So we have already seen the values of x has to be greater than 0. So the domain is open 0 to infinity. And what is the range of this function? Range is nothing but the values of log. What are the answers that you get? So we have already seen that when you calculate log continuously for different numbers, you get all the numbers from minus infinity to plus infinity. So when you go very close to 0, the value of log goes to minus infinity. When you go to infinity, the value of log becomes infinity. So the domain and range of the logarithmic function has to be remembered. And next, the graph of logarithm function has to be remembered. So how does the graph of logarithmic function look like? There are two possible graphs for logarithmic function. Depends on base a. So y is equal to log x to the base a if a is greater than 1. If the base is greater than 1, we have seen that as this argument increases, the value of log increases. If the base is greater than 1, then with x, y also increases. So how does the graph look like? Close to 0, the value will be close to minus infinity. Log 1 will always be equal to 0 at x is equal to 1, crosses the x-axis. And as x tends to infinity, the value of log goes to infinity. But as you see the values of log increases very slowly. So the graph looks something like this. So the graph is an increasing graph. That is, as x increases, y increases. And it always cuts x-axis at the point 1, 0. And as x goes close and close to 0, the value of logarithm goes to minus infinity. The value of logarithm goes to minus infinity. And as x goes to infinity, the value of log goes to infinity. These are the things that you need to remember. But this is when a is greater than 1. So the same graph, if you draw log x to the base a, if a is in between 0 and 1, this becomes a decreasing graph. And as x goes closer and closer to 0, if the base is a fraction, the value goes to infinity. Value goes to infinity. So the graph starts from here and goes on decreasing. It becomes 0 at x is equal to 1. That is compulsory. That is, it passes through this point and then goes down to infinity on this side. So the graph this time goes from plus infinity to minus infinity. And this is a decreasing graph. That is, as x increases, the value of y decreases. As x increases, the value of y decreases. But this also passes through 1, 0. This is a decreasing function. This is when a is greater than 1. This is when a is in between 0 and 1. So a greater than 1 and a is in between 0 and 1. So you have understood what the definition of the function is. You have understood what the domain and range of the function is. You have understood what the conditions are for log to be defined. And you have seen the graph of the logarithmic function when the base is greater than 1 and the base is in between 0 and 1. These are the things that you need to remember in logarithmic function. So now let us do some questions on logarithmic functions and conclude this topic. So in this question, you're given a quadratic equation in terms of log x. You're asked to solve this equation. So first this is a quadratic equation. So first let us say let log x to the base 10 is equal to t. So what does this equation become? This equation becomes t square minus 5t plus 6 is equal to 0. T square minus 5t plus 6 is equal to 0. So if you solve this quadratic equation, t minus 2 times t minus 3 is equal to 0. this implies t is equal to 2 or 3. So if t is equal to 2 or 3, that means log x to the base 10 is equal to either 2 or log x to the base 10 is equal to 3. So this implies x is equal to, I'll just convert this into exponential form. Log x to the base 10 is equal to 2 implies x is equal to 10 square or x is equal to 10 cube. So these are the two possible answers to this equation. So next, let us try to solve log x to the base 10 is greater than 5. Log x to the base 10 is greater than 5. So if you convert this into the exponential form, you get x is greater than 10 power 5, right? This 10 goes to this side, so x is greater than 10 power 5. So you have to be careful with this operation, because when you have an equality here, you can always do this. 10 power 5 is equal to x. But we have not said any property which relates with inequalities. So does this operation valid for inequalities also? You have to be careful here. So the property says that if the base is greater than 1, then you can directly do what are you doing for equalities, for inequalities also. So if I have a different question where log x to the base half is less than 4, so I cannot directly convert this into the exponential form. So if the base is in between 0 and 1, you can convert this into exponential form, but remember that you need to reverse the inequality. So if the base is greater than 1, then you can do the operations exactly as you have done for equalities. So if the base is in between 0 and 1, what you need to do is, you can convert this into exponential form, but you need to reverse the sign. It is x is greater than half power 4. Half power 4. That is, x is greater than 1 by 16. So this less than has become greater than. So that's the difference between equalities and inequalities. Thank you.